Hey everyone, and welcome to another visual journey on The Explainer. Today, we are going to unpack some incredibly fascinating everyday science. We're talking about the literal science of mixing, stuff that's happening right now in your kitchen, out in local lakes, and even in the medicines we take. Let's just dive right into the amazing world of solutes, solvents, and solutions. Okay, let's start with a mystery I bet you've experienced at least once. You're making a cup of tea, you want it nice and sweet, so you stir in a spoonful of sugar. Boom, it vanishes. You add another, vanishes again. But what happens when you add just a little too much sugar? Suddenly, it just stops dissolving, right? It kind of just sits there at the bottom like a pile of wet sand. So how does that actually happen? And is there a way around it? Keep that in the back of your mind as we go.
Which brings us to our first section, the science of mixing.
Right off the bat, there's a distinct difference between two categories of mixtures. If you've ever had an oral rehydration solution, an ORS drink, you know that every single sip tastes exactly the same. That's what we call a uniform mixture. The salt and sugar distribute themselves perfectly throughout the water. But if you try to mix chalk powder or sand into water, it doesn't just disappear. It stays all messy and uneven. We call that, you guessed it, a non-uniform mixture. And this really brilliantly illustrates the wild behavior of those non-uniform mixtures. On the left, we've got sand and water. It completely sinks and forms this muddy pile at the bottom. But over on the right, we've got sawdust and water, and it's doing the exact opposite. It's just floating up at the top. So why does something sink while others float when they refuse to mix? Well, we're going to solve that puzzle a little later when we get into density.
Moving on to section 2, solutes, solvents, and solutions.
So when we're talking about uniform mixtures, these are the two absolute core terms you need to remember. A solute is the substance being dissolved. Think salt or sugar. The solvent is the substance actually doing the dissolving, like water. And when you combine a solute and a solvent perfectly together, you create a solution. To really wrap our heads around this, let's zoom all the way in. Imagine the yellow spheres here are our solute, and the blue spheres are our solvent. Notice how the solute particles perfectly hide and just space themselves out evenly among the solvent particles? This perfectly even distribution is exactly why you can't see the salt once it's mixed into the water. It's like a giant microscopic puzzle fitting together. But wait, there is a super fascinating exception to how we define these terms. Check out these gulab jamuns dipped in shashni, or sugar syrup. Normally, we think the liquid is the dominant substance, right? Like the solid is just a minor addition. But in this rich syrup, there is actually a larger amount of solid sugar dissolved into a smaller amount of liquid water. It's crazy, but scientifically speaking, water is still considered the solvent here, and sugar is still the solute.
All right, section 3, pushing the limits.
Remember our team mystery from earlier? Well, here is exactly what's happening. When you first add a little salt or sugar to water, it's an unsaturated solution. Basically, you have a dilute solution because the water has plenty of room for more stuff. But if you keep adding more and more solute, making it highly concentrated, you eventually just hit a brick wall. The water simply cannot take any more at that current temperature. The solute stops dissolving, settles at the bottom, and boom, you've got a saturated solution. But there is actually a really cool scientific cheat code to bypass this limit. If you add baking soda to water at a room temperature of 20 degrees Celsius, it eventually saturates and stops. But pop it on a burner and turn the heat up to 50 degrees, and suddenly that leftover powder dissolves. Heat it up to 70 degrees, and you can dissolve even more. For most solid substances, heat literally forces a saturated solution to act like an unsaturated one. It's a total game changer.
Now, that is how solids behave. But let me throw a wrench in the works here. Does temperature affect the solubility of gases in liquids the exact same way? Think about natural bodies of water for a second.
Well, the answer is yes. Temperature does affect them, but in the exact opposite way. The solubility of gases actually decreases as the temperature rises. And this is a totally crucial twist of nature. Cold water holds much more dissolved oxygen than warm water. Even though it's just a tiny amount, this uniformly dissolved oxygen is absolutely vital for sustaining fish, aquatic plants, the whole shebang underwater. Let's jump into section 4, the secrets of density. Have you ever wondered why an iron rod feels so much heavier than a wooden stick of the exact same size? It all comes down to density. Imagine a bus packed shoulder to shoulder with people. That's high density. An empty bus? Low density.
Or actually, think of a dense forest crammed tightly with trees versus a really sparse forest with lots of open space. Density is simply just a measure of how tightly packed the matter inside an object actually is. Scientifically, it's a super straightforward calculation. Density equals mass divided by volume. Mass is how much matter is there, and volume is how much space it takes up. This handy little equation lets us precisely calculate heaviness completely regardless of an object's shape or size. Now, scientists love a good benchmark, and water is pretty much the ultimate one. 1 milliliter of water has a mass of almost exactly 1 gram at room temperature, which gives it a beautiful, perfect density of 1 gram per cubic centimeter. Because it's a perfect 1, we can easily compare everything else to it. For example, aluminum has a density of 2.7 grams per cubic centimeter. So its relative density is 2.7, meaning it is exactly 2.7 times denser than water. Okay, rounding out with section 5, measuring mass and volume. First up, measuring mass, which again is the quantity of matter in an object. We do this using a digital weighing balance. The golden rule here, always remember to press the tare or 0 button after placing your empty container down, so you're only measuring the substance itself. And a quick fun fact, mass and weight aren't exactly the same thing. Mass is the amount of matter, while weight is the actual force of gravity pulling on that matter. Next, we need the bottom half of our equation, volume. Volume is simply the amount of 3D space an object occupies. We usually express this in cubic centimeters, milliliters, or liters. To measure the volume of a liquid, we use a measuring cylinder. It's a tall, transparent tool with markings going up the side. The real trick to reading it accurately is to first note its maximum capacity, say 100 milliliters. Then look really closely at the space between the big numbers, like between 10 and 20. If there are 10 division lines in between, that means each tiny line represents exactly 1 milliliter. Getting that right is absolutely crucial for accurate science. So we know how things mix, how to manipulate their limits with heat, and how density dictates if they're heavier than water. But I want to leave you with a bit of a provocative thought today. The source text notes a really brilliant caveat. Density is not the only factor that decides if an object floats or sinks in a liquid. Weight, no way, right? But if density isn't the only rule of the game, what other invisible forces are at play out there? I'll let you ponder that little physics mystery. Keep exploring, and thank you for joining me on this explainer.